Alright, so we are going to start study guide 4. It's about conjugation, resonance, and dienes. So let's review nomenclature. There are 6 steps for naming dienes. First, as always, we need to find parent hydrocarbon. But specifically, it should include both C double bond, C bond. So you may need to turn corners to find the longest continuous carbon chain, and in a tie choose the chain with most branch points. So that's the first step. Second step, number the atoms of the main chain. Begin on the end closest to the double bond, and in a tie begin on end closest to the first branch points. Third, identify the number of substituents. Use your memorized names for the substituents and write the names in a single word. Hyphens separate prefixes, comma separates numbers, and list substituents in alphabetical order. Use di, tri, tetra if there is more than one of the substituents, and no space or dash before the parent hydrocarbons. That is the fourth step. And the fifth step is indicate the first C that is in the double bond by number. If more than one double bond is present, indicate the position of each and use one of those suffixes, diene, trine, etc. Alright. And for 6, for a cycloalkene, the number of carbons in the ring, number the carbons in the ring so that the double bond is between the C1 and C2 and the first substituent has the lowest number as possible. Remember, you do not need to indicate position of the double bond. Alright. So those are the rules and we are going to apply in below exercises. So, this compound name, we can see that 2-methyl 1,3-diene. So, you can see the main one, buta 1,3-diene. 4 carbon chain, 1, 2, 3, 4, buta 1,3-diene. And there is a 3 methyl group on carbon 2. So you can name that following the rules that we discussed. This one, cyclohexa 1,3-diene. This is 1, 2, 3, 4, 5, 6. So you can see 1,3-diene and there is a cyclohexane. Alright. Now 4E, 6E, 2,3,5 trimethyl octatriene. So there is 8 carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8. Alright. You can number it. Let's see. This is 7, so that's not it. Let's see this. Let's find out the other possibility. So what is the other possibility? 1, 2, 3, 4, 5, 6, 7, 8. Yes. Okay, I'm going to select pen. Alright. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's the maximum we get. And remember, there is a 2, 3, and 5 trimethyl, right? Now 2, 4, 6 triene. 2, 4, 6 triene. And when you look at 4E and 6E, so that is E position, that stereochemistry position that you need to find, and you can label it accordingly. Alright, now provide names of the following molecules. We are going to work on this problem. This is hepta-1,5-diene. So heptadiene, but it's 1 and 5. So you try to number them. Alright, so it's a heptadiene, but it's a 1 and 5. So that's why diene, 1,5-diene. Alright. Cyclopenta, 1,3-diene. So when we number it 2, 3, 4, 5, or you can number it, sorry. So you can see 1,3-diene, but it's cyclopenta. Alright. Let's draw 3Z, 5E, 3-bromohepta, 1,3,5-triene. So remember, we need to draw for the hepta. So it's a 1, 2, 3, 4, 5, 6, 7 hepta. Alright. And then you can see 1, 3, 5 trines, right? And you can see 3Z and 5E. So you need to draw stereochemistry in that. Alright. Sorry, let's go to further. Alright, next page. What is conjugated system? So it is an at least double, single, double bond. So C double bond C, then single bond and double bond. And you can see O double bond C, single bond C, double bond C. Now it has at least 3 sp2 carbon next to each other. So that is allylic carbocation, C double bond C, single bond C, positive charge. Now draw the following structures and circle the one that are conjugate system. Which one is conjugate? Remember, it's alternate. So there is a double bond, single bond, double bond. So that is conjugate. This is not conjugate because double bond here and here. When you look at 3-but 1 on, so double bond, single bond, double bond. Alright. Benzene, alternate single bond, double bond. Cyclohexadiene, 1, 2, 3. There are 2 single bond, and so that's not. So that way you can find the conjugated diene. I'm sorry, this should be the diene one. Okay. Alright, so there are 4 kinds of conjugated systems. Conjugated dienes and allylic carbocations we are going to discuss in this chapter. Conjugate polyenes responsible for many colors such as lycopene, red pigment in tomatoes. We will see on page 677 in your textbook. Conjugate enone, common in biologically important molecules. See cortisone on 674 on your textbook page. And cyclic conjugated molecules, next 2 chapters. Alright, now we are going to draw resonance, and I already draw it here, so you just need to see how the electron is flowing. Draw the resonance structure for the following carbocations. This is sp2 carbon, sp2, sp2 carbon, and there is a positive charge. So there is a intermediate float of, so that positive charge is right here, and then it will go here. So that's one of this resonance, and that positive charge moved to this side, sp2 hybridized carbon. So you can see the shift is on here. Intermediate is right here. So you can see that's another resonance structure. Why are conjugated dienes are special? Two conformations are possible for 1,3-diene, S-cis and S-trans. And you can identify each one in this diagram. So you can see the cis. This is a cis where two are on the same side. But what is S-cis? There is a single bond and there is a double bond attached. They are on the same side, so that's why it's S-cis. They are going, there is single bond and you can rotate. S-trans, and you know the trans, one is on the one side, another one is on the other side, and there is a double bond in between. But in here, S-trans means there is a single bond here. The double bond is on the one side and other double bond is on the other side, so that is S-trans. Alright, the single bond between two double bonds is shorter than the other single bond. So you can see this single bond is 148 picometer while the single bond is 153 picometer. So single bond is larger between the carbon, then this is the double bond is shorter because of this double bond is making a shorter distance between them. Alright, now let's go to dienes are more stable than expected heat of hydrogenation. The smaller the enthalpy, the more stable the compound structure. Now, relative energy of isolated conjugate dienes. So you can see isolated dienes, and this is the energy, but this is isolated conjugate diene. So less stable diene, more energy release, and delta H is negative to 225.5. Alright. The smaller the enthalpy, more stable the structure is, compound is. This is conjugate dienes, more stable 9. Less energy is released. So you can see when it's released and becomes single bond here, delta H is negative 226 kilojoules per mole. In this one is negative 255 kilojoules per mole. This is isolated dienes and this is conjugated dienes. So you know that conjugated is alternate here. So that is more stable than isolated one. Which diene has larger heat of hydrogenation? Explain. This one or this one. Remember, we just talked about that the more stable is conjugated one. This is isolated. So this is conjugate diene. They are stable. Then isolated diene. Alright. So that's why these are more stable. So this is the least one. Least stable. That's what it's asking in this question. Why is a conjugated diene more stable? So let's talk about it. The reason number 1. Comparison the hybridization of carbon in single bonds is identified below. So let's identify the overlapping orbitals in this bond. So you can see sp3, 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 sp3. While in here sp2, 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 sp2. Since sp2 orbitals have more s character, 33%, than sp3 orbitals, 25%, the electrons in sp2 orbitals are closer to the nucleus, and the bonds they form are somewhat shorter and stronger. The extra stability of conjugated diene results in part from the greater amount of s character in the orbital, forming the C bond C single bond. That's one of the reason. All right. Now let's see reason number 2. Illustrate the pi bonding. So you can see when you have this one and we are drawing its orbital diagram, notice electrons are spread out or delocalized over the entire framework rather than localized between two specific nuclei. Electron delocalization always leads to lower energy and greater stability of the molecule. So that's another reason. All right. Okay, let's go to next. Okay. Now the reactions of conjugated dienes. So there are 2 reactions that you need to memorize for conjugated dienes. The first one is electrophilic addition to conjugate diene through allylic carbocations and Diels-Adler reaction. Alright, so electrophilic addition to conjugated dienes through allylic carbocations. So electrophilic addition to conjugated dienes will yield both 1,2 products and 1,4 products. We need to show this reaction with 1,3-butadiene. Alright. So step 1, butadiene with HBr, it gives allylic carbocation intermediate. So when HBr is going to react with one of this pi electron. So pi electron is going to pull this proton towards itself. It breaks, this bond breaks and forms the carbocation right here. Okay. And when this allylic carbocation intermediate is resonance stabilized, so you can see it's resonance stabilized, the halogen adds to each cation to form 1,2 and 1,4 products. So there is one resonance here, carbocation, and one resonance here. This Br minus 1 is going to add to here. This Br minus 1 add to here. So that's why it's 1,2 adduct, 1,2 adduct, and 1,4 adduct. Now when you add hydrogen bromine to 1,2, it's kinetic product form. If you add hydrogen bromine to 1,4, it was thermodynamic product forms. So that's why you can see 1,2 and 1,4 addition product forms. Now the reaction becomes more complicated when 2 different allylic carbocation form. There are 4 possible products. So let's work on a problem. Give the structures of likely products from reaction of one equivalent of HCl with 2-methyl 1,3-cyclohexadiene. Show both 1,2 and 1,4 adducts and key to problem solving. Key to this solving problem is stay organized. So now you know that this is a pi electron is going to pull the hydrogen from the chlorine and the chlorine will have its electron back. This Cl minus, now as soon as the carbocation forms, this Cl minus attack and form the bond here, that is 1,2 adduct. Alright. Now, if we have, this is 1, 2, 3 and 4, when it reacts with HCl, there is a 1,4 adduct forms. This is 1,2 adduct. How? Because Cl minus is going to attack this carbocation right here. And then you can see how the electron transfer and forms the 1,4 adduct product. Okay. So this is more explanation. I would highly suggest when you draw and follow how the pi electrons from the conjugate system is going to attack and form the allylic carbocations and then Cl minus attack, and how the product forms. 1,2 and 1,4 product forms. This is another right possible products that are obtained from 1,3-pentadiene reacts with one equivalent of HCl. So this is pentadiene, 1,3-pentadiene reacts with HCl and it gives 1,2 adduct, 1,2 adduct, and this is 1,4 adduct. So that's again it comes with practice. Alright, let me scroll. Kinetic versus thermodynamic control. So when you observe the yield of these following reactions, remember at low temperature, negative 80 degrees Celsius, and at high temperature 40 degrees Celsius. At low temperature this product is dominated, and at high temperature 1,4 product is dominated. So predominates at low temperature, predominates at high temperature, 1,4 adduct 1. Remember we discussed about thermodynamics and those control. So let's go here. You can see the reaction coordinate and energy diagram A through B. You can follow the blue line and you can see this blue line, it lowers the energy, activation energy, while this red line it has higher activation energy. So lower the energy, more the product. So and faster the reaction, forming kinetic product B, and this is the slower reaction. So let me just erase so you will interpret. You can see that the blue line and red line. The faster reaction, which is kinetic product B, forms. Remember, activation energy is lower for the faster one, and for the slow reactions activation energy is higher. So when you look at for this particular product, let me go back here. Okay, so when you look at particular reactions, there is a carbocation forms at this point, and then you can see 1,4 product, thermodynamically controlled product, is lower in energy, and kinetic control, this 1,2 product and 1,4 product. So 1,2 product is kinetic, lower in energy, and thermodynamic one is more stable. So now why 1,4 product of 1,3-butadiene is generally more stable than 1,2 products? Alright, remember which one is more stable? Let's go back to here. We know that lower energy product is more stable, the red line one. So when you look at the faster the reaction, it's kinetic products. This one is lower energy, the stable one, the red line one, 1,4 product. So that you can explain. Disubstituted bonds are more stable than monosubstituted double bonds. Now go back to page 4 and label the product as thermodynamic or kinetic product. 1,2 product will always be kinetic, and 1,4 product can be thermodynamic if it is more stable. So that's something you guys need to do and apply. Now remember, carbon, 4 carbon ring, diene and dienophile, electron withdrawing, and it forms 6 carbon chain. So color code, so diene and dienophile, and when they react it forms the benzene ring. It was under the benzene it forms the cyclic product. So in 1950, the important reaction earned Diels Adler, a Nobel Prize winner. Why it is important? Because it forms in one step. It is one of the few general methods making cyclic molecule, and it is unique mechanism. is not polar or radical mechanism that you have studied, but instead it's pericyclic reactions. And pericyclic reaction, one is called diene and dienophile. Dienes and dienophile. So what is diene? So the diene must adapt what is called as-cis conformation. Cis like a single bond. As-cis conformation. And the S-trans conformation does not work. So this trans conformation does not work. S-cis conformation work because they work with these dienophiles. And dienophiles, there is a electron. Electrons basically moving. It's a marching around. All right. Now, some molecules can adapt as-cis conformation. They are more reactive in the Diels-Adler's reactions. So, as-cis conformation, and you can convert S-trans to S-cis. Some molecules are fixed in S-cis conformation and they are highly reactive. 1,3-cyclopentadiene is one of the examples. Some molecules cannot rotate as-cis conformation, therefore is unreactive in Diels-Adler's reaction. And some molecules cannot adapt as-cis conformation because of the steric hindrance problem. So they are unreactive in the reaction, Diels-Adler's reaction. So there are some of those. Now indicate the following substance can be used as a diene in Diels-Adler's reaction. Now when you look at this one, at this point, yes, it can rotate. Yes, this one. This one is locked in a transposition. One is this side, one is this side. So you can see this can kind of difficult. Now when you talk about dienophile, it's like alkene, the diene lover. They love dienes, dienophile and dienophile. So ethylene is non-reactive as a dienophile. Dienophile needs an electron withdrawing substituent group so that carbon next to the double bond is positively polarized carbon, and a carbonyl group or CN group are good electron withdrawing group. So when you draw 4 examples of good dienophile below, so you can see this is not a dienophile. Yes, this is a dienophile. You can see C double bond O. Right? Ethylene is not good dienophile. You see that carbonyl or cyanide group, anything, they are electron withdrawing group and they are good dienophiles. Now the stereochemistry of starting dienophiles, alkene, is maintained during the reaction, and you can see dienes, dienophiles, and cis conformation, dienes, and this is trans, and this is trans conformation. So whatever the conformation here, the product gain. This is Z, cis conformation, E, trans conformation. So draw the product form when each diene and dienophile react in Diels-Adler's reaction. So this is diene and dienophile, and when you look at diene and dienophile, the product will be this one. So you need to write how electron moves. So how you can number those? Remember, it's a 1, 2, 3, 4, 5, and 6. And remember, electron is moving in a concert reaction and they are forming a chain. So you assume this product. In a B, you number that. So the way you number it, this is, and the way you put it in a place, so that way it can start interacting. and as that you can see this one is going to join here and close the bond here. And so basically when you draw you will get better idea. But these are some of those answers I wrote, so you can check with that answer. When a Diels-Adler's reaction produces a compound that contains two fused cycles, a bicyclic compound with a bridge, the endo product is formed in higher yield. So when you look at the substitute in endo position, if it is closer to the longer bridge, the alternate position is called exo product. Alright, so you can see this is closer to 1C bridge. This is closer to 1C bridge, right? Z 2C in red, this is in red. Remember, this is the product when they react, it gives endo and exo1. Okay, so basically if it is it's closer to the 2C product and this is closer to 1C product basically. Alright. So retrosynthesis analysis and Diels-Adler's reactions. To find out what diene and dienophiles can be used to prepare a product via Diels-Adler's reaction, you follow these steps. Identify a 6-member ring that contains double bond. Draw 3 arrows beginning at the double bond forming 3 double bonds. Erase single bond lines and draw the double bonds to obtain diene and dienophile. An electron withdrawing substituent must remain in the dienophile. So these are some of those examples. And you can see the product. I would highly suggest when pause video and draw, so that will give you better idea. The answer is right here. There are other example as well. You can see. All right. So when you look at, give 2 different methods to prepare the following compound by Diels-Adler's reaction. So method 1, method 2 and method 3. You try to put all 3 methods and flow of electrons. You can see I draw the flow of electrons here and you can see the product forms. No, yes. Why? We follow these steps. So I would highly suggest understand this step, practice, and then pause the video and then try these problems on your own. The answer is given here. Alright, so we finished study guide. We finished study guide 4 and let's see.